All right, silly people, here's the situation. We have these two equations, which are the vector form of a Lorentz boost for Ct prime and r prime. Um, and we're supposed to be proving that we can combine these two equations into one equation just in terms of squared scalars on the right, which is r prime squared minus c squared t squared, or no, that's t prime squared equals r squared minus c squared t squared. Um, how do we do this? It took me a long time to figure this out. Um, so first, what you want to do is you want to um, completely square the second equation, right? We're doing r prime squared, which when we square that, it's going to be r squared plus, we're going to have beta dot r beta squared gamma minus 1 squared all over beta to the fourth plus beta squared gamma squared c squared t squared, and then the cross terms, so plus um, 2 beta dot r squared gamma minus 1 over beta squared. Um, minus 2, it's going to be minus 2 gamma ct beta dot r, and it's going to be minus 2 um, beta dot r gamma minus 1 times gamma ct. Yeah, okay. So let's combine then all the terms which depend on beta dot r squared and single beta dot r, and the terms that don't rely on it at all. So r prime squared then is r squared plus, yeah, beta squared, gamma squared, c squared, t squared, plus we're going to have beta dot r squared terms first, which include gamma minus 1 squared over beta squared and 2 gamma minus 1 over beta squared. And then we're going to have stuff that depends on only one power of beta dot r. And that stuff is going to be minus 2 gamma ct minus 2 gamma minus 1 gamma ct. All right, both of those terms inside the parentheses can be simplified, and we're going to do that. So r squared plus beta squared gamma squared c squared t squared. We're going to factor out a beta squared from this term here. Inside we're going to expand the gamma minus 1 squared, so it's going to be gamma squared plus 1 minus 2 gamma plus 2 gamma minus 2 in there. And then in here, we're going to have minus 2 gamma ct minus 2 gamma squared ct plus 2 gamma ct. Noticeably, this term cancels out this term. This term cancels out this term. And in the end, we will have r squared plus beta squared gamma squared c squared t squared plus beta dot r squared over beta squared times gamma squared minus 1 plus, or actually I'm going to do minus 2 gamma squared CT, yeah, 2 gamma squared CT beta dot R. Okay, let's talk about this quantity here, this gamma squared minus 1 over beta squared, which, using the definition of gamma, is going to end up being 1 over 1 minus beta squared minus 1 all over beta squared, which, to be fair, is going to end up being 1 minus 1 minus beta squared all over 1 minus beta squared, which simplifies again. That's going to be just beta squared up top divided by beta squared 1 minus beta squared. And then the beta squared terms cancel out. So it just ends up being gamma squared, which is pretty cool. Took me a long time to figure that out. So now we can rewrite the r squared equation as beta dot r squared gamma squared minus 2 gamma squared CT beta dot R. Okay, now let's turn our attention to the first equation that we were given, the time component of the Lorentz boost. So CT prime equals gamma CT minus beta dot R. We're going to square this term as well, and we're going to see something that's kind of nice. C squared T prime squared is equal to gamma squared C squared T squared minus plus gamma squared beta dot R squared. And it's minus 2 gamma squared CT beta dot R. Look at that. The cross terms match. That is, these guys match. So we're actually going to solve for those nasty cross terms and say that it's c squared t prime squared minus gamma squared c squared t squared is equal to gamma squared beta dot r squared minus 2 gamma squared ct beta dot r. And then return this expression to the r prime equation, which now is looking much, much simpler. R prime squared is equal to beta squared gamma squared c squared t squared plus c squared t prime squared minus gamma squared c squared t squared. Okay. Fantastic. Let's move the t prime squared over to the other side first. So r prime squared minus c squared t prime squared is equal to beta squared gamma. I'm actually going to say this. We're going to factor out a gamma squared, and we'll have beta squared minus 1 ct c squared t squared. Where'd my r squared go? Plus r squared plus r squared. Do you see this guy here? That's actually going to be minus 1. Gamma squared being 1 over 1 minus beta squared. If you multiply beta squared minus 1 times that, you just get negative 1. Pretty nice. Pretty nice. So we'll have r prime squared minus c squared t prime squared equals r squared minus c squared t squared, which is what Goldstein wanted. There you go.